So I guess we're going to start now since it is time. I guess maybe the TOC is the reason for this lower than usual attendance, but today's recitation is on Attack Lab. So your bomb lab is due tomorrow, remember that. That's the one we talked about last week. And Attack Lab is coming out tomorrow, so that's what we're going to talk about today. And you're going to continue to talk about stuff related to Attack Lab in class tomorrow. So what we're going to talk about the stack a little bit. And then we're going to do an overview of what you're going to have to do for Attack Lab. So Attack Lab has two parts. Attack Lab is a new lab this year. So the first three phases of Attack Lab, you'll be doing buffer overflow attacks. That's sort of a continuation of what the old lab we used to have, Buff Lab, was. But then we've added this new section, return-oriented programming attacks. This is completely new for Attack Lab. So if you remember from before, so there were some conventions about registers. Hopefully you remember at least a little bit of this from the bomb lab. It was relevant. So you have these you've got these 16 registers in x86-64, and some of them have special convention, special meaning. So your first 6 arguments to a function will be passed in these 6 registers in this order. So your first argument to a function is passed in an RDI, and then the next one in RSI, and so on and so on. The 6th one passed in R9, and then anything beyond that, 7 through however many you have, will be put on the stack. So this will be important to you because this is where your arguments come in. Remember that RAX is where your return value is always placed before you ret in a function. So the last thing a function does is it moves whatever the return value is supposed to be into RAX if it's not already there, and then it returns control to the calling function. Remember these two conventions about registers. So there's callee saved and caller saved. So did you talk about those two in class yet? Yeah. So does anyone remember what callee saved, what a callee saved register is, what that means? So when you make a function call, the control passes onto a new function, and that function is going to use registers, right? But you want to have some sort of way of not overwriting what was in those registers before, because you're going to return control to the calling function, and it might have some expectation about the registers are the same as when it made the function call, because it doesn't know what the function it's calling is going to do. So there's two conventions for what functions are supposed to do to make sure that their registers don't get overwritten if they want to keep them. So these 6 registers, RBX through RSP, are callee saved registers. So what that means is when a function is called, if it wants to use those registers, it is its responsibility to make sure that it saves a copy of them and restores it before it returns control to the calling function. So the function that is called has to save these registers. And then there's 6 other registers, or no, that's not 6, that's 9. There's these other registers that are caller saved, and that means it's the responsibility of the function that is doing the calling to save the registers. So if it wants to be using these registers after it makes the function call, it is the responsibility of it to make sure that it saves them to the stack before it makes the call and then restores them after, so that the function that it's calling can use them for whatever it wants. And then we have the RSP as our stack pointer. So RSP is the stack pointer. It tells us where the top of the stack is. Yes?
I'm looking at the caller save. So for those registers, the function, it pushes them onto the stack?
Right, yeah. So you've only got 16 registers, and you make a function call, and maybe the function you call wants to use all 16 of them. So you need some way to save this so that when you return, you haven't overwritten all of that stuff that you had.
My confusion was, why is it only those 6? Like you said callee save, so it's only pushing like RBX, R12, R13, or is it?
Right, so the registers are split into 2 sets depending on who's responsible for doing the saving. So you don't want to have to make one person responsible for all of the saving, because neither function knows everything about what the other function needs. So in order to not have to always save a bunch more than you might need, the responsibilities are split. And so the function that's called is responsible for those 6 there, and then the function that's doing the calling is responsible for the other ones in terms of saving them if they're needed. So then, a good compiler should say, if I'm a function and I don't need all 16 registers, the ones that I shouldn't use are the ones that are callee saved, because then I don't have to bother saving them. I'll just leave them as is, and when I return, I haven't touched them at all. And okay, so then there's the stack pointer, points to the top of the stack, and then the instruction pointer, which you can't read to or read from or write to directly, that tells you where you are in your program. And then there's the stack. So the stack grows downwards. It grows from higher addresses to lower addresses. And the top of the stack is pointed to by the stack pointer, where the top of the stack means the lowest address because it's growing downwards. And so we have 2 special assembly instructions, push and pop. Both of them just take 1 operand, which is a register. When you push, it subtracts 8 from the stack, which means it makes it 8 bigger because it's growing downwards. And it puts the value in the register at that address. So whatever value is stored in that register is written to that top slot of the stack. And then when you pop, you also give it 1 operand to register, and it takes whatever value is at that address of the stack pointer and it reads it into the register.
What if the register that you're pushing or popping, or I guess only in the push operation, is not a 64-bit register? So if you're pushing like EBP or something onto the stack.
Right, so with the 64-bit machines, the push and pop instructions are for 64-bit with registers, so you push the whole thing, even if you're not using the other 32. If you actually put in your assembly push EBP, the assembler would yell at you and tell you that there was a mismatch. Yeah. Okay, so that's push and pop. Any other questions about push and pop? You'll be seeing some of these in Attack Lab. Okay, so then every function manages its own stack frame then. So what you end up getting, is each function expands the stack as it goes, and so the stack ends up, you can partition it into a bunch of frames, 1 for each function in your that you've currently gone through. And so up higher in higher addresses, so deeper into the stack, lower on the stack, is the frame for whatever the function that called you is. And then even lower than that is the function that called it. And then you get to the frame for your current function. And so what that frame will contain, it contains your local variables, the saved registers that you had to save to make this function call. It contains the arguments that you needed to push to the stack beyond the first 6 that were passed in registers. Contains the return address that you're going to go to. So here's the diagram of how it's laid out. So this is sort of important here, and this is going to particularly the fact that the return address is up there is going to be something that you're going to be using a lot in Attack Lab. Any questions about stack frames? So, okay. So when you make a function call, the caller allocates some stack frame to save registers, to put the extra arguments in. It saves the registers that it needs to save. And then it's going to push the instruction pointer to the stack, which is going to be your return address. Because where you currently are is where you want to return to. You want to return to right after that call happened, and then it's going to jump to the label of the function that it's calling. So it sets the instruction pointer to the code at the start of the new function that you just called, and then that function is going to push any registers that it needs to save, and it's going to make room for whatever local variables it wants to be able to store on the stack. That's what happens when you do call. And then when you return, you increase the stack pointer. So you set the stack pointer now to a higher address, you've essentially removed that space from the stack for those local variables since they're no longer in scope. And you pop those registers that you saved so that they're restored to what they were before for the caller function. You have to do this in the reverse order that you push them on in, of course, because a stack is, it reverses things. And then you execute the return instruction. So what the return instruction does is it pops the address on the top of the stack, and then it goes to that address. So return is sort of just a shortcut for that. Does that make sense, how that would get us in and out of a function? Okay. So any other questions about stacks, function calls, how they work on the machine level? Okay, so attack lab. So attack lab split into two parts, phases 1 through 3, and then phases 4 and 5. So phases 1 through 3 are a buffer overflow attack. So what you're going to be doing is you're going to be doing an exploit that works by overwriting the stack, by writing too far, farther than it should. So here's the handout for BuffLab. What you can see here, so there's a function in C called gets, and what you do, you give it a buffer, and what it does is it reads characters until it gets a new line and puts them in the buffer. But this function has no way of knowing how big the buffer it is, the buffer that you gave it is. Because the buffer is just some sort of array, and it doesn't have a size associated with it unless you've kept track of that. But the gets function doesn't take any size or anything. So what can happen is if you give it a string that's longer than the buffer size, it'll just keep writing to the stack. And it'll overwrite stuff that it shouldn't be overwriting. It'll overwrite stuff that isn't part of that space allocated for the buffer. So if you remember back here, our little diagram, we've allocated some space down here for a buffer. But then if we keep writing, what happens is eventually we start overwriting the stuff up there, including the return address. And that's sort of the key idea in a buffer overflow attack, is that we can actually make the function go to a different place than it was supposed to by carefully constructing a string that overwrites the stack with something that when it goes back to that point will cause it to do something different than what it was going to do before. So we can overwrite the return address with a new one and exploit our function that way. Right, and we can also put additional code into the stack and actually have our program return to that code that we've written onto the stack and make it execute that. And so then we can execute whatever we want. We can write our own code into this string, shove it on the stack, make it return to that, and then it will run our code. So, okay. So how are we going to do this? So there's a couple, the bomb lab, you learned how to use object dump with the -d flag to disassemble stuff. You learned how to use GDB to look at stuff and figure out where the stack is being stored and what addresses things are going to be put on. You'll want to be using those again to figure out where exactly you need to be putting the code that you want to be running and the return address. Right. Okay. So this is this is the idea of the buffer overflow. Is that we have this space for the buffer allocated, but if we write past where it's allocated, we can overwrite the old return address with a new one that does whatever we want. If we want to inject new code to execute, you can figure out exactly how you're going to set that up to put new code in that spot and execute that. Right. So one of the things we'll want to be able to do, if we want to be able to make our own code and put it on here, put it in this buffer and execute it, we'll need some way to take code and turn it into the correct, bytes that the machine actually uses. Because what we're putting in is a sequence of bytes, a string, and we need to put in the bytes that correspond to code. So what we want to do is we want to use GCC and object dump to figure out what the byte code is corresponding to a particular assembly sequence. So say I want to write up some code. So I can open up, it's a bit bigger. I can open up in my text editor a file, and I'm going to give it a .s extension because that's the extension used for assembly, so I'll get the right syntax highlighting. So say I want to write some code that maybe it does a, I don't know, maybe I just want to do a move from RAX into RDX, and then I want to do a, I don't know, maybe I want to add 5 to RAX, or maybe RDX, and then return. So this is just some code that I decided I want to write, and I want to be able to put this code in the string so that my program will execute it. So what I need to do is I need to tell GCC to compile this to object code. So the -c flag will give us the object file for it. So you can see now I've got a file foo.o. And then with object dump, which we used before, with the -d flag, I can look at foo.o. And what we see is that it's given me the bytes corresponding to these assembly instructions. So the byte sequence corresponding to move RAX to RDX is 4889C2. And then this add is 4883C205. And then the return is C3. That's the code for return. And so now I have this sequence of bytes. What I can do is there's a program hex to raw that will take a hex sequence and turn it into a string that we can pass into our program.
What arguments did you pass to GCC?
So GCC, I gave it a -c. Yeah, and that'll keep the object file around for us. And this is in the handout too. Yeah. And then with object dump, it was just -d again, which is the same one we used for BottomLab. So you should be familiar with that one. And we could actually put this into its own file. And then the hex to raw program will take in these hex characters. And we're also actually able to put comments in the hex to raw program. So I'm going to leave these as comments here, so that I can remind myself of what this code was for. And then if I do hex to raw, we can look at what it takes. If I give it -i foo, then it gives me back this string. And so I'm going to pipe the output of hex to raw to my target for the lab, and this string corresponds to that sequence of assembly bytes. And you can see, there's like these question mark characters in, and that's because some of these bytes don't correspond to the normal printable ASCII characters, and that's why we use this hex to raw program. And some of them are the special control characters and stuff that you can't normally just type in. Okay, so we can generate the byte codes for an assembly sequence. We type out what we want, we run it through GCC and then object dump, and we get these byte codes for it. And then we'll pass that in to our program, and we'll pass in whatever string we want, and hopefully we overwrite the right parts of the stack with the right things, and then we'll have an exploit, and it will do something interesting. But buffer overflow attacks are actually not as useful these days as they used to be, because the people who designed the hardware and operating systems and everything got clever and realized that there's ways to sort of prevent these, even if the people writing the programs aren't 213 students who know to protect themselves against these attacks. So what's happened is new security features have been implemented. So like a stack, the location of the stack will be randomized with every execution of the program. And now we can't just put in a hard-coded address of where things should return to and get to some spot on our stack because that's going to be different every time we run the program. We can't run it once, figure out where it is, and then know that. And also the stack can now be marked as non-executable, so any code on any bytes in the stack won't be executed as code because that's not what the stack is supposed to be storing anyway, so it's probably a bad thing if your program is trying to do that. So of course, someone came up with an attack that gets around that. And so that's phases 4 and 5 of this lab, is return-oriented programming. So, okay, so essentially what we're going to do is we're going to make what are called gadgets. And these gadgets are going to be sequences of bytes that end in C3. So C3 is the encoding for return. If we went over, if we look at this again, we see that a return got encoded as C3. That's the byte code for return. But the thing is, C3 doesn't only show up exactly when you have a return, because maybe your instruction is adding a constant or storing a constant that happens to have the byte C3 in it. So we can actually get C3s elsewhere in our code. And if the code immediately before that C3 happens to also encode an instruction that's useful to us, then if we start execution there, we'll do that, and then we'll do a rec command. And what return-oriented programming does, so that's a gadget, and what return-oriented programming does is we're going to chain these things together and hopefully find enough that we can chain them together in some way that we can actually get something interesting to happen by executing code that already exists in the program, except that we're not executing the code that was actually the code that was written. We're just going to bytes within the code and using them as new code. So we're going to do an example of this if that doesn't make sense quite yet. Right, so we're going to sort of mix together pops and moves and constants to perform a task. Right, so there's in the handout, we sort of have a diagram of this. So sort of what we do is we have our stack, and on our stack we're going to put addresses to these little gadgets. And each gadget ends in a C3. Each gadget ends in a return. So our stack is some sequence of these addresses. And so the gadget 1 code, so what happens is we execute the gadget 1 code. It does its thing, and it returns. So what does the return do? A return pops an address off a stack, and it executes the code. It goes to that and starts executing the code there. So if we line these gadgets up on the stack, what happens is the gadget 1 code executes. We return, which pops off the address of gadget 2 from the stack, because that's what's next on the stack. And it executes the code of gadget 2. And then we've got another return, so it pops off the code of the address of gadget 3 from the stack and goes there and executes its code. And we can string together however many of these we want to just execute these little gadgets over and over and over until we've strung them together in a way that's caused us to do something interesting that we wanted to do. So here we want to do an example. So we've found 2 gadgets in the code, and we're going to show you how to find these gadgets in just a moment. But say we found 2 gadgets, and the one gadget is a move RBX into RAX and then return gadget, and the other gadget is a pop RBX and return gadget. And we want to take this value 0xBBBBBBB, and we want to pop it into RBX and then move that into RAX. And we want to figure out how we want to write to our stack so that this is going to be the effect that happens. Okay, so we've got a stack here. So we've got a stack. What sort of things, and we're writing, we've got this buffer that we can write to we're going to overflow it. What should we write? Any ideas, at least? Like, you don't have to have the whole answer yet. What sort of things do we know about the order we want to sort of put these together in?
We know that if we stick the number we want onto the stack and then call gadget 2, it'll get inserted into RBX.
Right, yeah. So we want to somehow get this value. We want value b, 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 b on the stack right before we call the gadget at address 2. Right. Yeah. So, okay. So what order then are they going to be on the stack? So I have some things on the stack here, here. So I've written this value, a bunch of b's. So where am I going to put the address 2 for the gadget with respect to this? So remember that as soon as we start executing gadget 2, it's going to do its thing. And this is some random piece of code, so it's not like playing with the stack because it's not a proper function. It's just going to use whatever the stack happens to be.
Should be directly above.
So directly above meaning above like this one, or above as in like higher in the stack? Because remember, this is the top of the stack. Yeah. So which one?
Say like on top of it.
On top of it, okay. So we're going to put the address for gadget 2 here. Let's put address right. Yeah. So address 2, we're going to put address 2 here. Okay, so when we get to this bit, what's going to happen, so assume we're executing this, we've somehow made it execute this, then what it does is it's going to do a pop of RBX, so it pops this off, and then it returns. So it's going to pop the next thing off the stack and go to that. It's going to pop this and go to that address. Right, because it's popped this off, and now this becomes the top of the stack. So the next it pops this off, it goes to that address to start executing. So what do we want to be right above B, 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 B? Yeah? Yeah, so here we want address 1. So address 1. So we put address 1 there, and so we'll execute this. We pop B, 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 B. We then, we have a return. So what does the return do? It pops the next thing off the stack, which is going to be address 1, and starts executing that. So now we go to address 1, and address 1 does move RBX into RAX, and then it returns. Okay, so then once we've done that, we've done what we've wanted. We've gotten we've gotten this value into RBX, and then moved it from there into RAX. Okay, so this is part of what we're writing. We're writing to a big buffer, and we sort of want to line this up into the right place, right? What do we want this over here to align with? So we're trying to get the normal function to do this instead of what it normally would have done. So this slot here used to be something else on our stack. What is it that we want to overwrite with address 2?
Return address.
Yeah, so this is what the old return address was. So if we put this where our old return address was, then we'll end up executing this rather than just going back to where we were supposed to go before. And then we need to, since we're writing to this buffer, we have to have some sort of filler. We allocated some amount of size for a buffer, and we just fill it all up with junk, and then start overwriting these things up here with the actual interesting code. So we want to pad it with however much padding we need to get it here. And that's going to depend on the size of the buffer, which you'll have to figure out by playing with it in GDB to see what that size is. Yeah, so here we have this example, and over here we can have more address, whatever we want. So we fill up the buffer with extra bytes until we've filled it up enough that the next thing we write is going to overwrite the old return. So we encode into the string that we're putting into this buffer into this overflow the address of the second gadget, and then this constant, and then the address of the first gadget, and then anything else that we want to do. And so then once this function executes, it fills, it goes and it goes to return back to where it's supposed to return, but now we've got a new address there. So instead it goes and it executes the code from gadget 2, which pops this, and then the return at the end of gadget 2 causes it to pop this and go to gadget 1. And then we can continue and chain them on until we've done whatever we want it to do. So does this example make sense to people of sort of what we've done? And since these gadgets, the actual code of these gadgets is part of the normal code of the program, then this gets around the fact that we're not able to execute code on the stack, because now we're not putting code on the stack to execute. We're actually executing code from within the program. And we don't care exactly where the stack is. We just care about the size of this buffer so that we can get the right offset. So this gets around the flaws that allow you to do parts 1 through 3. Okay. So how are we actually going to find these gadgets? So when you download your attack lab, there's going to be a file in it called farm.c. So this is your gadget farm. So we put this special file in here, and you should just look for gadgets in this. All the gadgets you need will be in here. Don't look through the rest of the code or try to find gadgets in that. So farm.c, if we open it up, it's just got a bunch of kind of uninteresting functions. They're just returning constants, and they're adding stuff, and they're setting some pointers and stuff. Nothing particularly interesting, but somewhere in here will be all of the gadgets that you need to complete the phases. And so what you want to do is, so it's like before, you can compile farm.c, and then you can look at what's inside it. Oh, I think I messed up. So now we can look at what's inside it. And we can see that there are, there's C3s in here. And the C3s in here are more than just the C3s that correspond to the original returns. So, we've got this C3 here, and this was just, the C3 from return. We've got this one here. But we've also got this 3, or no, that's not C3, that's 3C, that's backwards. If we look through, here we have one. So here we have a C3. And so this could be the end of a gadget, potentially. Any of these C3s could be the end of a gadget, but some of them will actually show up in places where there wasn't a return before, because this constant happened to have the byte C3 in it. And so what you want to do, so in the handout, we've listed out for you the byte codes for the different moves and pops and different things that can happen that you can use as gadgets. And so that if you have, so over here, a move from REX to REX would be encoded as 4889C0. So then if you had that right before a C3, then you could jump to that address. And what would happen is you'd execute that move, and then you'd return. So that could be a gadget in your chain. That one's not particularly useful because you just move something into itself. But maybe we want to move REX into RCX. So we would want to look for that sequence of bytes right before a C3. And then the address that that's at, because this is at some address in the code, would be the address that we can put on our stack to start that gadget. So you see how you can sort of get the byte sequence for a file to look through for gadgets. And it's these C3s. The C3s are what you look for, because that's going to be at the end of every single gadget. You want to go through and look for all the C3s, because all of your gadgets are going to end with one. And we can see, there's more here. There's another one there, another one there. Surely some of these are going to be something useful to us. Okay, so that's how we find gadgets. Right, so, okay. So we've talked about these tools. So we know how to take the file, take an assembly file and get an object file from it with gcc-c. So that's if we want to take our own code and figure out what the byte sequence for it is. We can also use gcc-c to figure out what the byte sequence in the gadget farm is. We can use object dump then to view those byte codes in the assembly instructions, and then we can pass that to hex to raw in order to actually get the string that will pipe into our targets. So you'll get two targets with the C target and R target. So C target is the target you'll be using for the buffer overflows, tests 1 through 3, and R target is the one you'll be using for the return-oriented programming. So we do C target. It tells me my cookie. Every one of you will have a unique cookie that'll be a value that's important for you to get on the stack or whatever to signify that you've done this. And it asks for a string, so I can put in whatever string I want. And this string happens to not buffer overflow or do anything useful. It just returns like normal. If I put in a longer string, put in something really, really long, then I caused a segmentation fault. What I did is, I overwrote too far, but I overwrote with complete junk. And so I overwrote with the return address with something where it just jumped to somewhere random that wasn't, valid memory to be jumping to. And apparently it was unable to send in the result or anything. There's no explosions on this one. It's not like Bomb Lab. It doesn't hurt you if you get it wrong. There's no deduction for it or anything. So, feel free to keep trying at strings as much as you want until you can, as you work on it and figure it out. You don't need to set breakpoints or anything. But of course, so what we'll want to do is, we'll want to be examining this, figure out what exactly the string needs to be, put in that byte code into a file, then we'll use hex to raw to turn that into the actual string that we'll pass to the program. And then hopefully we'll actually get a buffer overflow attack. And then with our target, it's the same thing, except now rather than doing it with the straightforward buffer overflow, we need to do this return-oriented programming attack. So we look for the gadgets and string them together to achieve whatever result we're looking for, and it's specified in the handout exactly what you should try to do. More instructions on what you should be trying to do with these. Okay, so any questions about this? Oh yes, a couple tips. Draw out these stack diagrams, it's useful. And be very careful of byte ordering. Remember from the first recitation we talked about little endian versus big endian. Remember that constants will be stored in little endian order. So when you want to have a constant loaded in, make sure you're putting the bytes in that order. Any questions? Make sure you read the write-up. It's got lots of useful things in it. It's probably got the answer to your question if you have one. Yeah?
When does the write-up come out? This week tonight, right?
It should come out tomorrow. Yeah, because Bomb Lab is due tomorrow. This one will be out tomorrow. Any other questions? None? Okay, then we're done a little bit early today. Good luck. Good luck with Bomb Lab if you haven't finished that yet.